Our today's guest is Francesco Dolce, who will speak about Lyndon words and Lyndon trees. So please welcome at the seminar.
So thank you. Thank you for inviting me, and thank you for attending this talk. Okay, actually the presentation has been done. I'm actually a postdoc here at the Faculty of Nuclear Science, but in a month I should join the FIT. Yes, today I will talk to you about Lyndon words and Lyndon trees. Now, I have to admit, I'm not completely sure about what you know about this kind of stuff, but I guess that since you do stringology or related stuff, you probably already heard of Lyndon words. But just to be sure, yes, I will, or just to be on the same page or to fix the notation, I will actually start this talk by giving the main definition of Lyndon word, where they are important, and how we can use Lyndon words to factorize the monad of all the words. It's called Lyndon factorization. And then I will talk about some more specific stuff relating to infinite Lyndon words or factorization of infinite words in general. And I will also introduce two things that are relatively new that we introduce via different authors. There are the so-called generalized Lyndon words, and then I will also talk about Cartesian trees and Lyndon trees. Okay, so let's start with the beginnings. So my main topic of research is actually combinatorics on words, and usually people get confused with what a word is, because of course everyone knows that a word is a sequence of letters somehow, and of course the words that are in Czech, like they are words, but in general the words that I'm interested in are just sequence of letters without any meaning attached to them. So they're just concatenation of symbols. These symbols we call letters from a finite or infinite, but let's say finite set of symbols called alphabet. And of course, we can have words with symbols from A to Z or A to J, but we can also sometimes use words just on a minimal alphabet. The minimal non-trivial alphabet is the binary one, for instance, 0 and 1. And this is quite useful when we do computer science, because computers usually talk between each other with 0 and 1s. Or we can use words when studying biology. For instance, if you want to consider a sequence of DNA or RNA, this now in fashion, we can use a 4-letter alphabet like ACGT and consider long sequences, calling long words. And interesting for me that I'm a mathematician, we can not only limit ourselves to finite words, as an example before, but also infinite words. This is an example of a binary infinite words, right infinite word on the alphabet AB. So it's something that here, of course, it's just the prefix. I cannot, since it's infinite, I cannot represent all the way of it on the slide. Another basic definition about slows, about words, is the one of factor. So whenever we have a word, we call a factor of a word just a contiguous subsequence of symbols that appears in the middle. Well, in the middle actually can be everywhere else. And actually we have two special names. Whenever this factor is at the very beginning, we call it a prefix, or when it's at the very end, we call it suffix. And also you probably noticed that here I use different symbols, sometimes a star from the alphabet, sometimes a plus, sometimes an omega. This is also another convention, because the star is whenever we consider finite words, including the empty word, like so on. The plus whenever we consider finite word, but excluding the empty word. And this omega here we use when we consider infinite words. In this presentation, write infinite words. And another convention is also that we use this notation with the bars when we want to talk about the length of a finite word. The length means just the number of letters that are inside. So for instance, are words of length 4, is of length 3. Here you have words of length 3, 6, and 9, and so on and so forth. Now, another interesting notion when we consider an alphabet just said it's a set of symbols, is that actually we can order this alphabet. And this is something quite natural because we do all the time. We say that A comes before B, B comes before C, and so on. But the interesting thing is that there is a natural way of ordering not only the letters, but also the words. Well, actually, there are several ways of ordering the words, but the way I will consider here is the lexicographical order. That is exactly the way that we learn how to look for words in the dictionary from when we were kids. So we say that a word U is smaller than V or comes before V if either U is a prefix of V, so V can be written as U followed by something else, or if U and V, they have a maybe empty common prefix, and then at the first mismatch, we have two letters A for U and B for V, such that A is smaller than B. I mean, exactly the order that you find on the vocabulary. So here is the basic example that I don't think I need to explain. A is a prefix of AB, so it's smaller. AB is smaller than AB because the first mismatch is the second letter, and you have A is smaller than B, and so on and so forth. Whenever we have a word, a finite word, we can also consider one of its conjugates. What is a conjugate? Well, a way of thinking about conjugates is that you take the words as a circular word, so you kind of bend it and connect the end with the beginning, and then you start reading from another position than the original one. Or if you want a more formal definition, you say that two words are conjugates if you can write one as a concatenation T and S, and then the other you just switch the suffix with the prefix. So for instance, here ABA is conjugated with AAB because here I switch AB, there is a beginning, I put it at the end, and A is at the end, I put it at the beginning. And ABAB, I could do the same thing. I switch A with BAB and obtain another word. We call class of conjugacy of a word the set of all possible conjugate words to W. So for instance, here ABA, according to where you start reading, you have ABA itself, but you can also have AAB or BAA. And for ABAB, you only have two possible conjugates. There are ABAB itself, and then if you start reading from the second, you have BABA. But if you start reading from the third letter, you have again ABAB, and then again BABA. So you have only two. Well, using this concept of these two concepts actually of ordered alphabet and of conjugation of words, Robert Lyndon and independently also Anatoly Shirshov in more or less the same years, they define an interesting class of finite words that we now call Lyndon words, at least because that's the Western version was the most spread ones, but you can also call the pravile slova, that's the original definition from Shirshov, or regular, correct, legal words. I don't know how to translate properly. So a word is a Lyndon word is, well, informally, it's the strictly smallest element of the conjugacy class. So you take all the possible words in the conjugation class, and then you pick the smallest one from using the lexicographic order. Some equivalent condition, actually, it allows you not to consider not to compare all the possible conjugation class, but just, for instance, studying the suffixes and the prefixes. So we say that the word is the Lyndon if for every factorization, non-trivial factorization PS, then you have one of the three conditions. Either W is smallest than its conjugate, so the definition that we saw before, strictly smaller than its conjugate, or W is strictly smaller than any of its suffix, the suffix part, so that's the final part in this factorization, or something that is not trivial at all. I mean, it's not that hard to prove, but you have to think a little bit about that. If whenever I consider this factorization with the prefix p and the suffix s, then the prefix is always smaller than the suffix. Just to give some example, every letter is of course a Lyndon word because we only have one possible factorization. The word AB is Lyndon because the only conjugate is BA and BA is bigger than AB. You can see that AAB and AAB, they also satisfy these three equivalent conditions. On the other hand, BA is not a Lyndon word because its conjugate AB is strictly smaller. And ABAB is not a Lyndon word because it's true that ABAB is smaller than BABA, but whenever you consider the factorization AB, and then you switch, we obtain again ABAB, and this is not strictly smaller. This means that every word that you can write as a non-trivial power of another word, will never be a Lyndon word. And actually, it's proved that Lyndon words necessarily must be the so-called primitive words, exactly. They cannot be written as integer power more than one of another word. Why are Lyndon words important? Well, actually, there are thousands of reasons, but an interesting reason for me is that actually Lyndon words, they allow us to construct a factorization of the free monoid. That means the factorization of the set of all finite words. And actually, the same Lyndon, Roger Lyndon, in 54, in the same paper where he defined the Lyndon words, he proved that every finite word can be factorized, and can be factorized in a unique way as a non-increasing product of Lyndon words. So W can be written as L1 and 2Ln, where all these guys here are Lyndon words, and the first one is greater or equal to the second, and so on and so forth. So just to give some example, the first word AACAB is a Lyndon word, so of course it's factorized as itself. BCBCA is not a Lyndon word, but you can factorize as a product of BC followed by BC followed by A, and these three are Lyndon words, and BC is equal to BC, and BC is strictly greater than A. And you can do the same for all the other words. And actually, what he proved that every single finite word can be factorized in such a way. Now, how to find this factorization is it's something that required a little more study, but actually Duval in 1980, he proved that it's possible to factorize. Not only that, but that we can do that in linear time. And actually, it's a very nice proof, and it's a very nice algorithm. I will not show you the algorithm, but just the idea of how to compute it. Well, first of all, the existence of such factorization. We first proved that it's possible to find factorization in Lyndon words, maybe not an increasing or a non-decreasing factorization, but at least factorization in Lyndon words. And this is just the trivial factorization when I pick as factors the letters, because we saw that letters are Lyndon words. So I have the first letter and the second and so on. And then we can cluster, we can aggregate these small factors to bigger factors using a property that is not trivial, we should prove it, that if I have two Lyndon words, U and V, and if the first one is strictly smaller than the second, then their concatenation is also a Lyndon word. So in such a way, starting from letters, I can construct bigger and bigger Lyndon factors, and having bigger or smaller and smaller Lyndon factorization. And how we prove that this algorithm stopped and actually find a unique factorization? Well, to do that, he proved actually that we have a condition on the first factor, and then by induction we can do on the same. And this condition is exactly that the first factor is the longest prefix of the word that is also a Lyndon word. So Duval proved that you can find an algorithm satisfying these properties, the existence of unicity, and you can do that in linear time. I will not give you the proof, but it's actually not hard to understand. Now, so far I talk about finite words, but the interesting thing is that actually we can apply some of these results also to infinite words. First of all, what is an infinite word? Well, as I said before, is a sequence of letters. Here is just a prefix, this infinite to the right. And an interesting way of constructing infinite words is starting from a finite word u and then just taking the infinite power. So when I write this u to the omega, it means the infinite word u an infinite number of times. Now, whenever we have an order of the alphabet, we can extend the lexicographical order that we saw before also to infinite words. And we can do exactly using the same, almost the same definition, saying that an infinite word u is more than an infinite word v if in our infinite vocabulary it comes before, and it comes before, it means that either is a prefix, well, okay, we cannot have a prefix of the other, but we can have that u and v, they starts with maybe some common prefix, p, could be empty, could be not, and then at the first mismatch a and b, I have that a is more than b. So just imagine your classical vocabulary, but with infinite words instead of finite ones. Whenever these two words u and v, finite words, they have the same length, then if I consider instead of u the infinite power u infinite times and v infinite times, I have that if u is more than v, then u to the omega is more than v to the omega and vice versa. However, it is important to note that this equivalence is true only if u and v have the same length, and this will come in hand in a few minutes. A counterexample is given by AB and ABA. AB is a prefix of ABA, so AB is smaller than ABA. But whenever I consider the infinite power, the omega powers, I have that AB is strictly bigger than ABA. Why is that? Because again, here starts with AB, so the fourth letter is B. The first two letters are ABA. And here I have ABA, so the first three letters are ABA, the common prefix is ABA, but then the first mismatch here I have an A. And since B is bigger than A, then I have this inequality. And well, you will not use this in the future, but it's nice to notice that actually two words, U and V, they have the same omega power. That means whenever I consider the infinite power, they are the same, if and only if, not only when in the trivial case where are the same words, but they can be different words, but they can be obtained as a power of the same word. Now, why are we interested in studying infinite words? Well, with a few years ago, a couple of years ago, with Antonio Restive and Christopher Adenauer, we proved this result that looks a bit technical, but it's actually not difficult to understand, and maybe with an example it will be better, that whenever I consider two finite words, non-empty words, u and v, then saying that u to the omega is 3 times more than v to the omega is equivalent than saying, well, all these other 5 possibilities. And let me show you in hand with an example. So let's suppose that they have the first word is just the letter A, and the second word V is the letter AB. We have that A to the omega is more than the AB to the omega. But this is equivalent of saying that the concatenation of UV to the omega is strictly smaller than just the second one, V to the omega. And this is also the same as saying that only the first one to the omega is strictly smaller than the concatenation V first and U after the omega. And this is the one that we are going to use soon, that when I take U and V to the omega, this is strictly smaller than the conjugate VU to the omega. But also that if I take just u, this is smaller than the prefix of uv to the omega, or that if I take vu, this is smaller than v to the omega. Now, let's focus again on the first and on the fourth. So it is equivalent saying that u to the omega is smaller than v to the omega, and that uv to the omega is smaller than vu to the omega. But uv and vu, they have the same length. And two words that have the same length, then considering the infinite power or just the finite word itself is the same. That means that u to the omega is smaller than v to the omega if and only if I have that when I consider u first and v after, this is strictly smaller than the conjugate. And if you remember how we define Lyndon words, that means that we have now 6 new, well, not completely new, I will say some word about 5, but new characterization of Lyndon words, because we know that a word W is a Lyndon word, if and only if for any factorization PS, I have that PS is more than SP, but this is equivalent whenever I consider PS itself or PS to the omega. And now we can characterize a Lyndon word also using the other 5 characterizations that we saw before. So W is Lyndon if and only if for any factorization PS, I have that the prefix, when I consider the infinite power, is strictly smaller than the suffix, infinite power, or all the others that you like, that when I consider the word itself, this is strictly smaller for this infinite word that only the suffix, or the 5, and actually this was rewriting and using our notation of an old result of Narowski, that when I consider the prefix alone to the infinite, this is strictly smaller than the word itself. Or you can play a little bit more and just considering the prefix and the conjugate, or the conjugate and the suffix. Why is that important? Well, it's important not only to characterize Lyndon words, but also for the factorization of any word in Lyndon words. Because this is just a rewriting of what, we're using our terminology of what Narowski proved in 95, that whenever we have a factorization of a word W in Lyndon words, the unique non-increasing factorization, then we can characterize the first element of this factorization, and we can characterize in different way. Well, either as the element such that is strictly bigger than the rest of the other elements, so all the other concatenation of all the other factors, that means the suffix when I consider the factorization. Or, and from an algorithmical point of view, this is more interesting, that the first element of the factorization, L1, is the shortest prefix, non-trivial prefix, such that is strictly, or is, well, in this case, not strictly, but is bigger or equal, greater or equal, than all the rest, the suffix for this infinite order, or is the shortest non-trivial prefix that is greater or equal, not only the suffix, but of the word itself. So let's work with an example. This is going to be a bit clearer. If I consider the word AAB, its Lyndon factorization, it's these 3 words. I have AAB, and A. And actually, I can find the first piece, this AAB, as the shortest prefix, such that AAB is, for the infinite order, is greater than all the rest for the infinite order, or the greatest than the word itself for this infinite order. So it's nice because we have now a way to characterize the first element of this factorization, and if we can characterize the first, then we can focus only on what remains, and then characterize again the first, and so on and so forth, and then we have an algorithm to compute this algorithm, to compute this factorization. Now, another interesting things that we define is the generalized Lyndon words. But before defining generalizing Lyndon words, I have to define what is a generalized order. So this is the definition on the left that we saw before. We say that an alphabet with an order, we say that the word U is more than B if in our vocabulary we can find either a prefix or we consider the first mismatch, and the first mismatch is such that the letter here is more than the letter B. But what if instead of considering just one order, like A is more than B is more than C, we decide to change this order for every position? That means that we define an infinite series, but a countable series of orders, and we say that U is more than B, either if U is a prefix of B as before, or U and B, they have a common prefix, and then the first mismatch are such that A is more than B for the order that corresponds to this position. So the first thing, of course, if we take the same order everywhere, then we just find again the definition of a classical order. So if A is always more than B, then we have no difference between a lexicographic order and the classical one. But we can also construct something different. For instance, we can decide that A is more than B if the position is odd, and the opposite, B is more than A, the position is even. In this case, we'll have, for instance, that, okay, A is a prefix on AB, so A is more than AB, but AB is more than AA because the first mismatch is in position 2, 2 is even, so we have that B is more than A. And then AA is more than B because in position 1 it was that A is more than B. B is a prefix of BBA, so B is more than BBA. But BBA is smaller than BA because the first mismatch is in position 2 and we have B is more than A. This is called alternate order and is actually very important, well, for many reasons, also for Lie algebras, but in particular it's important for people studying continued fraction because whenever we consider the numbers as letters in our alphabet, we can see that actually A1, A2, A3, we can stop or not, is smaller for this order alternate than B1, B2, and B3, if and only if the associated continued fraction, they are the first inferior is more than the second. But then of course we can just play and define new orders. For instance, this prime order is just a small modification of the alternate order. Let's say that A is more than B whenever we are in a non-prime position and B is more than A whenever it's prime. Or we can just invent an order according to our fantasy. Now, using this order, we can generalize different notions, including the notion of a Lyndon word. So, we said before that a classical Lyndon word is just a word such that is the smallest one in its conjugacy class. That means that for every factorization, the PS, we have that W is more than SP. Another way of saying that is exactly the same, is that since PS and SP that has the same length, then instead of considering the order, I consider instead of consider the word alone, I consider the infinite powers. We saw this is the same. Well, we define generalized Lyndon words if, for any factorization, we have the W to the omega is more than SP to the omega with respect to this infinite order. Now, we'll see why it's important to consider the infinite powers. But first of all, we proved with Antonio Restive and Christopher Rothenauer, and actually completing a result by Christopher Rothenauer alone, that a word is a generalized Lyndon word, according to this definition, if and only if we have, well, something similar that the definition that we saw before due to Roger Lyndon. That means that for any trinotarial factorization, we have that P is more than S for this generalized order, but when we consider the infinite powers, or if the word itself is strictly smaller than the suffix, but again, when we consider these infinite powers. we studied the generalized words and generalized Lyndon words, and we gave several results. And one of the results is connected to the factorization that we saw before, the Lyndon factorization. We actually saw that also using Lyndon words, we can factorize every word, every finite word, as a non-increasing factorization of generalized Lyndon words. And moreover, well, we already have, due to Fnarowski, characterization on the first element, L1, but we were able to give not only for the classical Lyndon words, but also for the generalized framework, a characterization of the last, the smallest, if you want, of these words. So if you want, we can start considering this factorization both from the left or from the right. Now we have two ways to do that. And if you're interested in this characterization, is that this ln is the shortest suffix, that is the minimum between all the shortest suffix, or this is also generalized Lyndon words. This is a technical thing. What about infinite words? Well, first of all, we should define what an infinite Lyndon word is, but we can do, there's a nice definition of an infinite Lyndon word. It's an infinite word that is strictly smaller than all its suffixes. So, for instance, if you consider A, B, 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 every non-trivial suffix starts with B, so it's strictly bigger than A, B, 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 B. And we can do the same for generalized Lyndon words, so using, for instance, the alternate order. If you consider A, B, A, and so forth, every suffix either starts with B, so that you have the first position B bigger than A, or starts with AA, so in the second position you have an A that is bigger than B for the alternate order. Well, an interesting result by Siromone, Matthew, there, Subramanian, is that you can factorize not only finite words, but also infinite words as a concatenation of Lyndon words. Of course, since we are talking about infinite words, then what does it mean to factorize as a concatenation of Lyndon words? Well, you can do it in two ways, either using only finite Lyndon words, and in this way you will have an infinite product of non-increasing finite classical Lyndon words, or you can use only a finite number of them, these Lyndon words, but the last one must be an infinite word. Now, Siromone, Matthew, Bramen, they proved in 2005 that this is possible. Given every infinite word, you can factorize using classical Lyndon words in one of these two ways. But what about generalized Lyndon words? When we published the paper with Christopher Denauer and Antonio Restivo, we actually let this as an open question. And we were quite surprised that in a matter of a few months, less than a year, two different teams of people, Postis and Zambon in France and Woodcroft and Winsor in the US, with two different methods, they found the same solution. So they actually proved that this is possible to factorize every infinite word as a unique non-increasing factorization of Lyndon words using exactly the same trick as before. That means either using an infinite number of finite Lyndon words or a finite product where the last one is an infinite word. Okay, well, the last topic that I want to talk, since it's spring, or at least it's supposed to be spring, I want to talk to you about trees. Well, okay, not this kind of trees that you see in the picture, they're really nice, but the binary, there should be a binary trees, complete binary trees. What is a complete binary trees? Well, you can define either as a letter or as a combination of two trees. So, okay, this is the formal definition, but that I'm sure you're all know. And whenever we consider binary trees, we have the classical notion of root, of internal node, and of leaf of a tree. So a root is a node that has no father, and a leaf is a node that has no sounds. And we also consider, whenever we have a complete tree, in this case binary tree, the foliage of a tree. The foliage of a tree is just the concatenation, essentially from left to right. This is the formal definition of all the elements on the trees on the last level. So for instance, here the foliage of this tree is causal. Now, what is the link with, how can we construct a tree using linear words? Well, first I should define you what is a left standard factorization. You maybe know about the right standard factorization, or maybe not, but the left standard factorization of a word is the factorization as prefix and suffix, such that the first part, this P, is the longest non-empty proper suffix that is also in the word. So for instance, if you take this word here, AAB, AAC, AB, you can see that the longest Lyndon prefix, proper prefix, is AA, B, AAC. And then I have something else, AB. You can give a lot of different properties. One of these is that whenever you consider such a factorization, then the remaining part, the first part, P, is a Lyndon word by definition, but the second part is also a Lyndon word. And actually, the second part is either just a letter, so you cannot decompose anymore, or you can decompose in such a way that the first part of the new factorization is treated as more than P. So in the example before here, I have that the suffix AB is a Lyndon word, and that AB you can decompose as AB, and A is treated as more than the first part of the original factorization. Why is this property interesting? Because usually this property, actually we can construct a tree starting from a Lyndon word. We construct the left Lyndon tree. Okay, I will show you an example, it would be easier. Let's pick again the Lyndon word that we saw before, AAB, AAC, AB. So what is this left standard factorization? Well, it's AAB, AAC on one hand and AB on the other. Then we split this and we consider on the left the trees obtained by the word AAB, AAC, on the right the word obtained by AB. And we stop, we continue until we find the letters. So for instance, AAB, AAC can be factorized as AAB, AAC. AB can be factorized as the letter A followed by AB. AB can be factorized by AB, AAC by AAC, and so on and so forth. Now, something that is maybe not completely clear, but not that hard to prove, is that the foliage, that means that the concatenation of all letters from left to right is exactly original, is exactly equal to the original word, the root. So the foliage of this left Lyndon tree is exactly equal to the Lyndon word we start with. This is the Lyndon tree. Then there is another structure that is based on prefixes. There's apparently an independent one. And to do that, I have to remind you what the prefix standardization is. But to do that, I have to use this order that is similar to the order we saw before, the infinite order. I consider U to the omega, V to the omega, with the little slight difference that whenever I have two words such that the infinite power is the same, then I consider the smallest one as the longest. So here, for instance, AA, if considered its infinite power, is equal to the A to the infinite power, but AA considered smallest to A. And then here you have that A is more than AB, AB is more than BA, AB is more than B. Using this order, we can associate to a word is called prefix standard permutation, that essentially just consider all the prefixes in order. And again, I will show you an example, it would be easier. Pick again the words A, B, A, C, A, B. The smallest prefix, according to this order, is the prefix AA. The second one is just A. Then you have that A is smaller than AA, BAA. And if you continue so on and so forth, you will see that you can construct all, you can pick all the different prefixes. And the last one, since this one is a Lyndon word, is the word itself. So you can associate to every word the permutation of the prefixes. And using this permutation, we can actually construct another tree. This is called the left Cartesian tree. And using again the fact that every Lyndon word is such strictly bigger than every of these prefixes, then we know that the last element of this permutation will always be the biggest number. So let's just forget about the last element of this permutation, because for the Lyndon, it's always be the bigger one. But then focusing only on what will be remaining, we can construct a tree in a very simple way. We pick the bigger element, so here is 7, this is the root, and then we consider on the left the tree generated by the permutation remaining, and on the right the one remaining here. So for instance, on the left on 7 you have 2, 1, 5, 4, 3. What is the bigger number? Well, it's 5, while on the right on 7 is 6. Now let's focus on 5. On the left we have 2, 1, so we pick the bigger number is 2, and on the right we have 4, 3, so we pick the bigger is 4. Then what about 2? Well, on the left we have nothing, and on the right we have 1. What about 4? We have nothing on the left and 3 on the right. And what we finally obtain is an incomplete tree, binary tree. And if we decide to complete this tree using in such a way that the foliage is the word associated with permutation, we obtain a new word. This is called the left Cartesian tree. This is important for a lot of structures. And what we proved, this is absolutely non-trivial, that whenever I consider this new tree, this Cartesian tree, and the Lyndon tree that we defined before, they actually are the same. So there is an isomorphism between these two trees, the one associated with the prefixes and the other associated with the permutation. Now, if this is familiar to you, is because maybe you read somewhere about the right Lyndon trees and the right Cartesian trees. This is a bit an older structure that some people starting from Christoph Hollweg and Christoph Rettenauer studied, and they actually proved that these two trees from the right, the one considering the suffixes, the one considering the right permutation, they coincide. How can we use this tree? And actually, I go back to last stringology that you held in Prague. You can, one way to use it, and is the way that Gomez, Batkoba and Maxime Cochemore use this algorithm, use this construction. You can actually generalize this construction using not only trees but forests, so not only using Lyndon words, but every possible finite word, because you know that every finite word can be written as concatenation of Lyndon factors. And using the algorithm we described before, then we can construct the Lyndon forest associated, and we can sort the prefixes, and most importantly, we can do that in linear time. I will not give the details also because if you assisted to stringology a few months ago, you probably already remember about that. But I actually think that I spoke for more than 40 minutes, so I will stop here. So thank you for the attention.
Okay, let's unmute ourselves to give an applause. So are there any questions? Okay, maybe I can try to ask them. So you use this generalized order on the alphabets, like alternating one and things like that. So like which of them is kind of the most natural, or where does it come from to use this different order on every position, or what's the motivation to do this?
Okay, well, the original motivation was algebraic one, because there are something related to Lie algebras. But actually, we found quite soon that there was another interesting motivation related to this small property. I spoke of it very quickly, but this is related to the continued fraction. And there is a whole community of people studying continued fraction, and it's very important for not only combinatorics and words or algorithms in general, but also for dynamical systems or numeration as well, actually. And so this is a positive motivation. But all the results that we proved, we actually proved not having in mind only this particular order, but having a general order that can be constructed anyway. Then it's true that this one is the one that we studied more, and actually we obtained, for instance, here we found a construction, sorry, a characterization of the the last or the smallest factor in the factorization, in the Lyndon factorization. You remember that there is already something for the first factor. Then we studied more in detail what happens when you consider the first factor, but only for this alternating order. It's actually what we call here, I haven't written anywhere, but the Lyndon words for this alternating order. They are so important that they deserve a special name. We call them Galois word. Again, because they're related to this stuff. So for this particular order, we studied more in detail, so we gave some technical result.
Okay, thank you. Are there any further questions? If not, then let's think again. Okay, so that's it for today, and the next week we will have the last seminar of this semester, and so we are looking forward to have you all here.